Good day, class. In this example, we're asked to find the derivative of a function. Now note, as we proceed in this course, there'll be other ways to find the derivative, but we must always keep in mind that by definition, the derivative of a function can be found with the same formula that we're used to. F of x plus h minus the function itself, f of x, all divided by h. So if we plug in this information and simplify, it will yield the first derivative of the function. So let's do that. We have the function and we have plugged in the information, except of course everywhere I see x on the first part of that example, on the first part of that formula, I'm going to input x plus h. So be very careful when you're doing this. Notice how I have a parentheses around the f of x, the function, that 9x minus 1 all divided by 7x plus 4. And I'm doing that because I want to be very careful and just respect that sign that's there. That negative sign can really throw off your entire ball game. So all I've done at this stage was substitute the function into the formula and respect the formula as it's given. Now I can begin to simplify. There's really nothing more to do except simplify. So I'm focusing on, there's nothing really can happen with the denominator right now, but in that numerator, I can go ahead and subtract those fractions. So in preparation for subtracting those, they're rational expressions, of course, but in preparation for subtracting them, I want to lose the parentheses. So I'm doing that. I'm going to distribute that 9 across that x plus h quantity and also that 7 across that x plus h quantity. And so when I do that, I peel this thing apart a little bit and then I go ahead and combine or get like denominators. And I simply do that by multiplying the denominator of 7x plus 7h plus 4 multiplied with 7x plus 4. And so I multiplied those denominators, but I still have to be respectful of the rules for multiplying, of subtracting fractions. So if we need to go back and review the rules of subtracting fractions, no problem, be sure to do that. But this will always get you there. Maybe you'll want to pause this video and just take a look at the pattern that was used to multiply these fractions, to subtract these fractions successfully using this technique of multiplying the denominator. So as I proceed, I'm going to distribute. So I'm just getting rid of those parentheses, but everywhere I need to preserve the parentheses just to remember, where are my signs? What do my signs, what terms do those signs affect? So I want to be very careful. So notice the placement of my parentheses, how I'm being very intentional and very careful with this material, just so I don't lose my signs, because all we're dealing with is algebra, but just a lot of it. So at this point, I'm preparing to subtract these two polynomials now. So I'll go ahead and do that. Notice how I distributed in that highest numerator. I distributed the negative throughout that second set of parentheses. And so that's all that's happened so far. And now I'm going to look for any like terms that can potentially be combined. And if you notice, and that's one beautiful thing about these polynomial, or the way these this procedure turns out, we get lots and lots of cancellation. So notice how that entire upper numerator essentially narrowed itself down with all the cancellations to 43h in the numerator, and that's all we're left with. So we look for that. If you don't have a lot of cancellations at this stage of your practice problem, it really means that you've probably missed a sign or something like that. So you want to be very careful with your signs. And then as we proceed, we have to deal with that upper denominator. And so I want to deal with that, but I still have that lower denominator of h. So I'm going to multiply the entire upper fraction by the reciprocal of the lower denominator. That h is going to now become 1 over h, and it's going to get multiplied by the fraction. Now I can sort of multiply fractions straight across, deal with that right away with no problem. It just pretty much shares that h across those polynomial terms in the denominator. And so now I'm looking for anything else that can cancel or simplify in any way. And so I've got h's that cancel very quickly. Many of them cancel, and so that leaves me with, from the numerator to the denominator, and so that leaves me with the 43 on the numerator and the denominator an even more simplified polynomial. And so now I'm looking for something I can combine or simplify further, and there's nothing right now. So at this stage, I can assume that I've combined and simplified everything. Now I can substitute that h, which approaches 0. Remember, as the we're looking for the limit as h approaches 0, and now if h becomes 0 in the denominator, I'm not dealing with an undefined expression like I would have been before I did the simplification operation. So now I can substitute h0 in for h, and we're rid of several of those terms, leaving us in the denominator with 49x squared plus 49 x, pardon me, plus 56x plus 16. And so now we can rewrite that if you recognize this as a perfect square trinomial, and go ahead and rewrite that denominator as 7x plus 4 quantity squared. And so this is the representation of the first derivative of our original function. So after that long and horrible method that we used in the previous slide, let's take a look at a faster method. In fact, I'm going to introduce you to some differentiation rules that will allow you to do this, what I've done here, with the very same problem and differentiate very quickly. And so notice how with all my notation and with all my details here and with a little algebra, I can resolve the very same problem, find the derivative of my original problem without all the hassle from the first slide. So let's go ahead and take a look at some differentiation rules. So sometimes you'll be asked to find the derivative of a constant. And so here's a notation type example, and or a theoretical example. And so in theory, the derivative of c, or the derivative of a constant, is equal to 0. And so let's talk about the reason for that. Let's say we've been given y is equal to 5, and we're asked to find the derivative. Now, quite often we won't be asked to find the derivative of y is equal to 5, but very often in this class or in this study, you'll find that a constant will be somewhere in your function, and you're taking the derivative of various parts of that function, and then one particular part that turns up could be a constant. And so just I want you to know going in this thing that you'll automatically write that as 0, or the derivative, or determine that the derivative of that value, that constant value, is 0. The reason why: recall what derivative means, or taking the derivative or finding the derivative. We're talking about the slope of a line tangent. In some cases, we could talk about the slope of a tangent line. So if you have y is equal to 5, notice it might look like this on a graph, but what does a line tangent to a horizontal line look like? Of course, it's also going to be a horizontal line, and if you recall from your study of algebra, the slope of any horizontal line would be 0. So if you want to find the derivative of y is equal to 5, then I could write the notation here: y prime is equal to, or I could also write the same notation, d over dx of 5. Okay, so we're going to study this notation throughout this lesson, and then that is equal to 0. So no stress over the notation. It'll shake out for you quite well as we continue to pursue this. Then we have the power rule. And so the power rule says that if n is a real number, then we can differentiate in the way that we see here. So essentially we have x raised to the n, or some base raised to a power. And on the right side of that equal sign, it's telling us what to do with that base and that power. So notice how that power sort of comes down and multiplies by the base, and then that power also loses a value. So if I have my equation here, y is equal to x raised to the 9th, and I differentiate, we're calling all this is essentially notation to sort of guide us and tell us what we're doing. then that actually becomes the derivative of this equation becomes, or the derivative of this line becomes 9 times x raised to the 8th power. Then we have the power rule. And so the power rule says that if n is a real number, then we can differentiate in the way that we see here. So essentially we have x raised to the n, or uh, some base raised to a power. And on the right side of that equal sign, it's telling us what to do with that base and that power. So notice how that power sort of comes down and multiplies by the base, and then that power also loses a value. So if I have my equation here, y is equal to x raised to the ninth, and I differentiate, we're calling all this is essentially notation to sort of guide us and tell us what we're doing, then that actually becomes the derivative of this equation becomes, or the derivative of this line becomes 9 times x raised to the 8th power. So let us consider the constant multiple rule. It's different than the constant rule we looked at a moment ago. And it says if C is a constant and U is differentiable, then we can do this. So remember, for this course, C is can obviously be a constant. We can notice that with no problem, but U is going to be differentiable. So we have this sort of caveat, but for us, it's always the functions that we're going to be working with in this course will always be differentiable. And if there's some quirk or something, we'll know about it in advance. So we can say if we're presented with a problem such as this, that then we can differentiate by just sort of pulling that constant off to the side, if you will, and sort of just dealing with it later. So that C sort of comes out, moves to the side, and then we differentiate the function that remains, or the piece of this function that remains. And so now we have, in our example, we have y is equal to negative 8 times x to the ninth. And if we want to find the derivative, remember we're looking for, in context, the slope of the tangent line, then we're going to find we're going to move that negative 8 off to the side, and we're actually going to differentiate the x to the ninth. And so in terms of manipulating, we're differentiating the entire function, but in terms of manipulating this thing, we're dealing with that x to the ninth, and that's what the constant multiple rule says we can do. So whenever you see the setup, just go ahead and pull that coefficient off to the side, and then we deal with the variable portion of it. And so now we learned about the power rule a moment ago. So now we know how to deal with that x to the ninth. We know that we can pull that 9 down in front of the x, and then we can lose one of the values. And so instead of not x to the ninth, we now have x to the eighth. And then, of course, we just simplify. So the derivative of this particular function is negative 72. Of course, we need to go back and multiply that negative 8 times 9. So we have, to simplify this, so we have negative 72 times x raised to the eighth. This is the slope of the tangent line. Now we have the sum rule. So the sum rule, this is another one that's very, very helpful. It seems very basic. When we look at it, we're really just talking about, we have the sum of functions, and if they're both differentiable, then they're differentiable separately. And so it just allows us to split them up and differentiate them apart from the plus that we have there with them. So essentially, if I have this, here lies a function, y is equal to negative 8x to the ninth plus 5, and then I can lay that out in function notation, or in using the notation for differentiation. And so I'll do that, but it looks really messy and very gaudy. But notice how I have, my initial indication that I'm going to differentiate the dy over dx. And then I have that is equal to d over dx of, and my function is there. And so the next piece, I'm just splitting them up and saying, okay, I'm going to differentiate them separately. These terms separately. The negative 8x to the ninth gets differentiated, and the 5 gets differentiated. And we dealt with those in the previous slide, so we know that negative 8x to the ninth becomes negative 72x to the eighth, and we know that that 5 goes to 0. So we're really just looking at the derivative of y is equal to negative 8x to the ninth plus 5. Well, we can easily identify the slope of the tangent line, which is going to be y prime is equal to negative 72/8 to the x. You may have assumed the difference rule works the same, and it does. Just like the sum rule, we can differentiate them separately and our terms separately and then come up with our first derivative.